track, for example, is it an electron or is it a proton? Is the current going into the field, is the current going out of that type of thing, direction of the current. Now, the AP Physics, this fourth block, has already bought their panel, so that's already taken care of. But if you want to order any solar merchant, I taught you all in the fall, but if you want something going off into college, the order forms are up there, or if you're going to go to Mom and Pa Kettle and go, hey, graduation is coming, I'd like to take something. So if you want to order anything, those forms there, I don't necessarily need the money by Thursday, but I need the order form by Thursday. So that's why don't feel neglected and go, oh, we're not up on the wall to get a panel. This guy's fourth block already has one. So, but if you still want to donate, hey, help me save the world. Okay, so let's chit chat about a couple of these problems. So let's talk about, say for example, number 18. Okay? So on problem 18, this is more of a visual type thing. So determine the magnetic field direction. Now here's the thing that you have to keep track of. You're asked to find the direction of the magnetic field that causes the charged particle to experience the indicated magnetic force. Okay? So if you look on 18A, first off, this is going to be an electron, okay, or at least a negatively charged particle. And the other thing that you have to pay attention to is that the vector that they're giving you is the velocity vector, okay? So on 18A, you've got a vector going, a velocity vector going this way, and it's an electron. You're also told that the magnetic force is out of the page, okay? So you have to be careful when you're dealing with like a two-dimensional space of the page of the book. So within the page of the book, Dan, did you start the camera?
Yep.
Okay. So within the page of the book, just so everybody's clear kind of on the axioms. So when you say up or down, I'm thinking you're talking about in the plane of the page, okay? So if you tell me up, I'm thinking it's going to be in the plane of the page, pointing up, pointing down. Then you could have into the page, okay, so that would be like going, like you're drilling into the page like this. Out of the page, I'm going to interpret as something like this, okay? So if it's in the plane of the page, which most of these are, then you can say, hey, is it up, down, 45 degrees, something like that. Okay? But if you tell me up, that means up like this. If you tell me out, that means it's literally coming out of the page. So I want to make sure everybody's cool with what I'm going to interpret your description as. Okay? Up and out do not mean the same thing. Okay? Yes?
For down, can we say like it's coming towards me? Would that work? Just stick with down.
Yeah, stick with down. Because I don't know where you are. Okay? So, yeah, no. Yeah. Coming towards me is no. I would probably discern it, but that's, yeah. Yeah, because then if you're upside down, then that gets weird, and anyway. So, you have the force coming out of the page. So there's a couple of things that make this a little sketchy, okay? First off, it's an electron. So I would recommend that you just start with the left-hand rule, okay? So on this one, if you go with the left-hand rule, start with your index finger, okay? That's going to be pointing this way. Now, this, you have to do a little bit of kind of like wonky stuff with this. So that's going like this, all right? So because it's an electron, and the force is coming out of the page. What it's asking for is the direction of the magnetic field. So remember, thumb is your velocity, your index finger is the magnetic field, these fingers are the force. So you kind of got to do a little bit of interpretation, like, okay, hey, what's that going to look like? So if you go with that and then coming out of the page, then which direction is that going to point? So just keep that in mind. So for example, on 17, I'll give you a hint. On 17, those answers are either out of the page, like for example, or towards the top of the page or into the page, something like that. Now, when you get to 18, with that one, that might be handy to give like an angle. So if you consider like this being like 0 degrees, if you go old school with how we define vectors, you know, it might be like, 90 degrees or 270 or something like that. So that might be handy how you define those directions. Now, let's talk about the numeric answers on 8 and 9. And this is where science, and this is more of a societal thing as well. So if you look on number 8, it says magnetic fields generated by transmission lines, okay? So, you know, you've all seen them. We have to have them because we generate electricity in one big power plant, and then we distribute it out. Okay, cool. So as that electricity gets distributed, it makes sense to transmit high voltage lines and high amperage lines, and then you have to step it down before it goes into your house. So that's what the transformers do. So have you ever seen like those kind of like gray cylinders that are up on the telephone poles? That's what those transformers will do. They're stepping down that voltage and that current down to 120 so you can use it in your house. You don't go to like, I'll just get electricity direct from the source and I'll plug a wire into the transmission line. Bad things are going to happen. So what some people will say is like, okay, cool. Well, oh my God, there's a magnetic field around them because it's a current. And it is, okay? Admittedly, there is going to be a current. And everyone goes, magnetic fields are bad. It's like, stop. This is why I purposely picked these questions. It's like, right now, you are being subjected to a magnetic field, okay? It's a good thing, all right? The Earth has a magnetic field. We want a magnetic field. This is why we're says, let's colonize Mars. Mars doesn't have a magnetic field, which means if you're on the surface of Mars, which you couldn't be anyway, but even if you could and it didn't have a magnetic field, the sun has a mass ejection of highly charged particles. There is nothing to protect you from those charged particles like there is on Earth. So, what you need to do, and this is the whole point of this, is that both of your answers, or 8 and 9, are the exact same. Okay? So here's the point, is that you laying underneath a heated blanket is going to be subjected to the exact same magnetic field as standing underneath the transmission line. Okay? And both of those are only 4% of the normal Earth magnetic field. Okay? So everybody says, what is the magnetic field from transmission line? The field from the Earth is 96% times greater. You don't see people flipping out, oh my God, we got to stop the Earth's magnetic field. No.
Let's do that.
Good luck with that.
Good luck trying. You're going to do
Okay. Now, what?
What do you consider positive Y and negative Y on 22A? Beat him up, Bird.
Okay. On question 22,
Yeah.
okay, I would consider the way that that's defined, positive Y would be going like into the page, negative Y would be coming out of the page.
Oh, okay. So it's positive Y. Okay.
Okay? On that one, it's just probably easier if you say into or out of the page. Then there's no real ambiguity.
Yeah, it's just like
Okay. Now, let's talk about question 25 in terms of how this plays out, oddly enough, with our magnetic field. So, here's the deal. So, you've got our strange rock, and it has a magnetic field. And again, don't flip out. What we call the North Pole is actually the South Pole of the interior magnetic field, okay? Don't flip out over that going, oh, this is so weird. Well, that's just the way it is, okay? So, basically what happens is that our local star every once in a while flips out and goes, throws a little bit of a hissy fit, and it shoots out these charged magnetic particles. The worst one they ever had, at least in recorded history, how it impacted communications, was in the late 1800s.
Carrington event.
And so at the time, we had telegraph wires. Okay, we didn't have satellites, we didn't have cell phones, nothing, okay? And it was just wires, and it was literally telegraph with Morse code, and you tap out an electrical signal, somebody else would hear it, and you translate it back and forth into Morse code. So at the time, we had such a large solar ejection that it fried that system, okay? Like it overloaded it, fried the wires, bad things happened. And so the thought being is that if that same event happened now, like in a worst case scenario, number one, you're going to lose a lot of the satellites because satellites have no protection because they're outside of our atmosphere. Worst case scenario is that it fries the electrical grid. The worst case scenario I ever saw was that potentially the electrical grid would be down for a year before we got it back up and fully functional. So imagine like me even trying to teach in this room. I have no windows. I lose electricity, I cannot teach in this room. Okay, candles, yeah, I'd have to have candles or something like that. So, and here's the problem is that, hey, electronics are great, satellites are great, it's cool. GPS, all this stuff. But, Thatch.
Well, finish what you're saying, go ahead.
And that's great as long as it works. But imagine, and I was having this discussion with my brother the other day because we're kind of old school and we like maps and they're cool. But if I said, hey, you need to navigate to a particular intersection in Hutchinson, Kansas, just using a map, and it's like, what? It's like I got to keep track of where I'm at, and then I got to look at a map, and it's a whole skill set that is kind of lost. But it used to be literally people would have either like the Rand McNally was like the gold standard of atlases. And you would have the Rand McNally Atlas, and it had every state and every major city, and it had all the maps on it. But you had to keep track of like, okay, what intersection am I at? And you'd have to look on the map, and then you'd have to know north, south, east, and west, and which direction that you're headed. And then, because it used to be, because I've gotten graduation announcements from some of you. Thank you for that. But it used to be, when I started on the graduation announcements, it would list the address, and then it would give directions on how to get there. It would say, oh, if you're coming from the south, go north on 119th, turn left on 21st Street, take a right on whatever, look for the second right, okay? Nobody does that anymore. Why? Yeah, you just punch it into your phone, and the phone tells you how to get there. So it used to be on when people would send out like wedding announcements, graduation announcements, whatever, they would include written instructions on how to get to that location because you didn't have GPS. And now no one does it. It's like, oh, I need to get to, Connor S.'s graduation party. Oh, type in the address. Boom, the phone. And it even talks you through it. You don't even really have to be able to read a map. Thatch.
So if you hypothetically had a solar generator and then there were solar flares, would the generator work?
Defined by solar panels?
No. Well, it would have
What
solar
would
panels, obviously.
The solar panels would still be okay. The concern is that it isn't so much the solar panels, it's the connection to the grid, where that would get overloaded, and then you're talking about problems with the entire grid. The solar panels themselves would still be okay. But here's the problem. Like even with these solar panels, we can't run the school directly off of those solar panels because there's too much fluctuation. So the only way we could actually run the school from the solar panels is if we modulated it and ran it into like a large battery system. And the battery system then could regulate the flow of, a steady flow of energy out into the school. So solar panels themselves, you can't use it directly because it still feeds onto the grid.
Yellow.
Yeah, sounds like yeah, sounds like
Yeah. Okay. All right. Alex, watch the video, go to the side if you want. So you, that's the problem, solar is that, and the same thing with wind or whatever, is that you have to be able to have a steady outflow of that energy. Okay, so, back to our story. So on 25, that's a cool question. So, you've got the Earth's magnetic field, these charged particles are coming in, and here's the idea, this thing is going to be traveling in a circle. So you set the magnetic force equal to the centripetal force, okay? Because that's, and again, this is, I was explaining this to Lauren this morning, is that why is it the centripetal force one of the four fundamental forces of nature?
Say that again.
Why isn't the centripetal force one of the four fundamental forces?
Wouldn't they have to, like, wouldn't it be the similar to gravity in some cases, I guess?
Things are attracted.
What do you mean?
Like, for orbital motion, like, the force, the centripetal force is powered by gravity,
Yes.
so it's just.
So here's the anomaly of the centripetal force. The centripetal force masquerades itself as something else. It masquerades as gravity, or the electromagnetic force, or the tension in the string. So the centripetal force only ever exists if something else is there, okay? If there were no other forces in the universe, we would never know anything about circles. Now, here's an interesting thought. I read an interesting thing the other night. Speaking of gravity and centripetal forces. So, here's the Earth, here's the Moon, okay? So, and there's a few things that I read, I go, wow, that is just really, really cool. So I kind of nerded out. So, let's say that here's the Earth and here's the Moon. So the Moon is tidally locked to the Earth. So what that means is that the Moon takes about 28 days to go around in its orbit. But it also takes 28 days to spin on its axis. So what that means is if this is the side of the Moon that's facing us, that side of the Moon is the only side that we see. Now, if you're on the Moon, you see different sides of the Earth because the Earth spins 24 hours. So if you're on this side of the Moon, you will always see the Earth, okay? You will always see the Earth. But this is what I found interesting, is that if you're on the other side of the Moon, so let's say you were born, raised, you lived on the other side of the Moon, you would never know that the Moon is orbiting the Earth because you would never see it. So if you were there, you would just see, you would still have sunlight. It would take a long, days would be really long, okay? But you would, if you were on the other side of the Moon, you would never know that that Moon was orbiting a planet because you'd never see it. So it's like, that would be kind of weird, that you would never know that you're orbiting a larger
Space would spin
Earth.
around you, but you would never see the. Weird.
Yeah. Yeah, you would never see the Earth. Cohen's going, oh, just rock me to sleep tonight on that one. So, Cohen's mind is blown at this point.
think we need to get him a drug test.
Yeah.
Yeah, it's kind of cool.
Cohen is hot.
Okay, anyway, back to our story.
With respect to Earth.
So, on this one, you're going to set the QVB equal to the MV squared over R. The velocities, you're gonna cancel out one of the velocities. In this case, you wanna solve for R. And so you get R equals mv over qb. Now, here's the fundamental difference when you look at 25. On 25A, everything's gonna be the same except for that it's an electron. On 25B, everything's gonna stay the same, except now you're gonna use the mass of the proton. So that electron orbital radius is 0.1, should be like 0.1 meters, okay? 0.1 meters is about like yay. So the electron around would have an orbit of like this. The proton would have a radius of about 10 meters, which would be about from that side of the wall to that side of the wall. So the electron has this orbital radius, the proton has a radius all the way across the rim. But that's just because of that difference in mass. 21's an interesting question just from a historical perspective. So once they figured out, after Rutherford did his gold foil experiment, and you had the nucleus and you had the electron, okay, which even now is horribly out of scale. This is not to scale, okay? This is not literally. Like, I would have to go from here to here to represent the diameter of an atom, and the actual thickness of the nucleus would be a human hair right in the middle, okay? To put that to actual scale. That's why I said, if you think about too much what happens on an atomic level, you're just gonna end up in the corner sucking your thumb. Bad things going to happen. So one of the things they said is that, okay, first off, they figured out they wanted gravity to work because these were all physicists. They said, oh, we want this to be like the nucleus, like the sun, and the planets are gonna be like the electrons. Because everybody understood that. Everybody had studied Newtonian mechanics. Everybody had studied planetary motion. They said, oh, it's going to be like a little solar system. This is so cool. Okay? And they got all excited, but then they realized that's just going to be a train wreck because it's not going to work. So they said, okay, what if there's like a current inside of there? Maybe there's like something generated current that would create the magnetic field to hold the electron around it. So on 21, the first thing you have to figure out is the current. So that current is going to be like something times 10 to the minus third. Okay? And then the magnetic field to do that is going to be about 13 Tesla. Now, to give you some perspective, the magnetic field of the Earth is like 5 times 10 to the minus fifth Tesla. The magnetic, so imagine inside of every atom of your body, you have a magnetic field that is basically 1,000,000 times greater than the magnetic field of the Earth. Okay? It would be awkward. So you walk by anything metal, okay? And then you're just stuck there. So, and then you run into somebody else. Either you're going to be absolutely repelled or absolutely attracted, and either way, bad things are going to happen. On 22, that answer for the force using QVB should be something times 10 to the negative 13th. Okay?
22.
Your answer to 26A should be something times 10 to the 6th. Okay? 26A. You're only half done, so you're not there.
No, I'm there.
And your answer to 26B, this is an ish gap, Sean, should be around 800. 26B should be around 800. So, all right.
Energy conservation is alive.
Yes.
What did you get?
I'm not even gonna say it.
What did you get?
What did you get, Sean?
Oh, 3.2 billion.
That's the first time I've heard
I don't know.
A or B?
I'm pretty sure that literally.
On A, at least I'm somewhat right.
It's a,
but-
it's a
I'm close.
relative.
Yeah.
You did say
On
it.
A, I'm close.
It's an
close,
ish.
but-
You said it.
I did ish. I
You said
did say
it.
ish.
That is an
You
ish.
took ish to the extreme, but it's an ish. Okay, are we good? Once, twice,
Define good.
ish, sketchy?
Ish, sketchy, yeah, it's an ish.
Sketchy?
Within 3.2 million.
Conservation
go.
of energy.
Okay,
is a
all
lot.
right, get that handed in. Danny, stop me on the camera, let's go to the back of the room.